And it's very exciting to be here. I'd like to thank the organizers for inviting me. This is truly a delight. I'm a material scientist, so participating in a forum like this is a little bit foreign to me. And the first thing that I tried to do, at least to place this in context, was to look at the title of the conference, and so sort of imagine what I think that the innovative designing life and future could mean from my perspective. And innovative is something that we do every day, for sure in the lab. It's either by trying to find something new, or certainly what we do in our case is to reinvent something that has been around for a long time. The designing life part is very broad. And I think from a scientific standpoint, there are some very pragmatic aspects of designing life at its core, which can involve things like synthetic biology or tissue engineering, things that you implant that I will talk about, and possibly the way that you design sustainable resources or use sustainable resources. Whereas certainly life can be the design of life can be interpreted, I think, and you know this better than me, in distributed services and in global society and in social interfaces. The future to me, because of this material bias that I have, it might be more connected, whether it's on a human-human level or whether it's the human and the object. And the human and the objects are becoming much more connected right now. And you can see it possibly in your everyday life, where you talk, your cars, your phones are becoming much more part of you. So the challenge is, are we going to be able to think about materials that are going to affect the way that you connect with fixtures or homes and buildings or larger infrastructure? So materials today, the status quo is that materials today for the most part are immutable, and they are very stable in their behavior, and they are disconnected from living matter for the most part, and they use a lot of non-renewable resources. And generally, the form of the material determines the function of the material itself. And materials tomorrow, I think, are going to be materials that are self-healing, that repair themselves, that transform themselves, that are very sensory, that disappear harmlessly, and maybe that are sustainable. But we cannot sacrifice the technological performance that we're used to. So we want to keep them at that level. And perhaps the form of the object will not reflect its function. And so the segue for me is, I've had this collaboration. I've worked with Silk for some time. I've had this beautiful collaboration with Neri, and I want to tell you a little bit about Silk. Silk is a material that we love very much, and how we think that this is a 5,000-year-old innovation in a certain sense. And you've seen the pictures, the images of a Bombyx mori silkworm. Here it is again. And so the message here is trying now not looking at the swarm as an additive building environment, but focusing on the silkworm as a chemical factory and as a material generator, and as a generator of a very powerful material that is polymorphic. So from the same starting point, a material that can do many, many things. And our process of transformation is that we go back. So we take the cocoons that we unraveled on stage today, and we boil them, and we melt the fibers. So we remove the sericin that was the glue that was talked about this morning, and we get a liquid silk solution, just like the solution that is in the glands of the silkworm. And then we use this solution as the starting point for multiple forms of silk. And the multiple forms that we have are very vast. So micro and nanoparticles, sponges, films, coatings, blocks, and ropes, and so forth. And I want to just go through an image gallery of these forms because I think it's instructive. So this is, for example, a 100% silk moldable plastic sheet, so to speak. Plastic, obviously in quotes. You can do these things. Photonic elements. My background is in photonics, and so this is a credit card that is made 100% out of silk, and that you can store information in. So you can read it out optically, like you would a DVD, in fact. So you can write in various languages digital optics. So this comes from the fidelity of being able to reshape the material on the nanoscale. You can do holograms. So this is a very large, this is a 12 by 10 centimeter image that is written on a film of protein. You can mold the protein so that it assumes a microneedle format. You can do what the worm does and take that solution and repull and redraw a fiber. And in this case, we want to make optical fibers to guide light. Then you can do blocks. So you can do, for example, gears and nuts and bolts and solid mechanical components. So these are all, again, 100% fibroin. They can be molded in tubes, such as this that we use for vein replacements, or in larger molded parts, such as bones. Or we do experiments where you actually try to make functional structures, like, for example, a maple seed. And you see here, this is from a museum exhibit that was curated by Thomas Duggan, and that's what you see on the right is the image of the silk maple seed flying. Cups. And then we can also, because of the technical aspects of silk and of the quality of the material, we can interface metals to it. So in this case, we can build sensors or formats of electronics that are unusual, implantable, flexible, and that can be interfaced with light. So these are many forms that are becoming progressively much larger. At this point, we can make rolls of film, much like plastic. The question is, why would you want to do these things with silk? And so I think the function comes in, and the function of this material is what is the real differentiator from conventional materials that you have today. All of the processes that you've seen before to make these materials are water-based. So the process is quite sustainable. The material is edible. It's implantable. The technological part, I say it's technological because we can do these things with optics and electronics. And another important aspect is that it preserves the biological function of materials, of the dopants that you mix. And so when you have all these forms and you mix them with all of these functionalities, what you get is very unusual material outcomes. And it's a particularly interesting connectivity between the biotic and the biological, the natural world, and the inorganic world and the materials world. So the so-called biotic, abiotic interface. So these materials that become it's a true playground for the material scientist, because you can start thinking of how to put things together and how to make unexpected materials, a form that behaves in a way that you didn't imagine before. And I think that the two themes are embedded materials, so materials that can be embedded environmentally and be resorbed in the environment, or biologically embedded, or just materials that you can use every day. I want to stress some of these augmented functions just to see, because I think that they are important and they do have some societal impact. One of the probably most impressive augmented function pieces is that if you mix biological matter into this liquid silk solution that you have, and it's simply like mixing a drink, then when you have your doped solution, then you can go back and go into all of these forms that I've described before. Whatever is mixed in is stabilized. So you have a very nice way of maintaining the activity of these biological dopants. And so what we did is, for example, we looked at stabilization of vaccines. And the first experiment was storing penicillin, liquid penicillin, that becomes inactive at room temperature in 2 days, whereas we made films with liquid penicillin that stabilized penicillin for 2 months at 60 degrees Celsius. So then we looked at measles, mumps, and rubella vaccines, and these are this is a very important societal impact if you think from two aspects. One is that you can break the cold chain, and there are many kids that need global access to vaccines. And the second thing is that also you improve your logistics, because you don't necessarily need the vial that we show here. You actually can store vaccines in films, and it becomes much more convenient to transport if you solve some of these issues. Other augmented technologies, you can add life to ordinary technology that we have in our desktop. So we can, but with the same principle of stabilization, we can generate a bunch of functional inks. And the functional inks are, for example, things that enable you to do things like this, where you can print therapies. So this is the printed logo of a university close to MIT. Here we are printing antibiotics. Silk stabilizes an antibiotic. The antibiotics are released on a bacterial. The bacteria is killed according to the pattern that you print. At the same time, you can stabilize a lot of chemistries on paper, and you can turn paper into a multidimensional biological sensor. And you see an image here of these inks with an enzyme that turns color. And this was very interesting. We did it. We did this reasonably recently, and we had this concept of sensing paints that we looked at in the past with Emily Joko, who's an architect from New York. As her master's student program, she was imagining a bridge that would monitor pollution through these sensing elements, through sensing paint that was distributed on the walls of the bridge, and that could emanate through scattering the status of particulates or the status of pollution that was present in the atmosphere. And so right now we are looking at actually this gas sensing through paintable and printable silks. The other things that you can do is you can look at human interfaces. How do we become more integrated and more communicative? And so we look at the features of, for example, conformality of silk. You can control the way that the material bends depending on the way that the proteins bind together. And so you can go from a rigid state to a very supple state where you adjust the mechanical properties, which means that you can interface with I apologize for the image, but you can interface with very low mechanical modulus surfaces like the surface of the brain. And this is a sensor, this is an interface that actually detects EEG signals in vivo from the surface of the brain, being able to follow the curves of biological tissue. And you can start thinking also of having more communicators. So the thing that you can do is you can become a transmitter and a sensor at the same time by integrating these materials, for example, on your teeth or on your skin, which are some of the things that we do. Other examples of where you fall in, not only on the surface, but you become biologically embedded, is, for example, use the fact that the material is edible. And so in this case, you see gold leaf garnish on a chocolate cake. Instead of having these sheets of gold, you can shape the gold like an antenna. And what you see here is this. You see this little antenna that is put on the surface of a slice of cheese, and this is the signal that you detect for all intents and purposes with a cell phone. And so it tells you whether there's bacterial buildup on the cheese and whether the cheese is fresh or contaminated, and you could eat it with the cheese if you so desire. So this brings in how you affect logistics chain, how you do smart packaging, and how you do sensors for health monitoring and food safety, which are very, very important for the future. This is an image of part of 100,000 antennas on the surface of an egg. And then lastly, I think we want to figure out how we control materials so that they disappear. We are challenging also the paradigm of electronics. And instead of having, the design rules that are typical of microfabrication and of silicon circuit design, we want to make electronics that dissolve on command. And the reason that we want this is twofold. One, therapeutic, and the second one is environmental. You can imagine that there's a lot of electronic waste that we could mitigate by exploring this type of approach. So what you see here is you see this little small chip that you see here on the finger is a wireless heater. And it's a wireless heater that is made of silk and magnesium. Magnesium is a salt that you find in your body. Silk is a beautiful material. And what happens here is that this heater gets implanted under the skin, and then you close up, and then wirelessly it gets powered on, it heats up, and it kills bacterial infection. So if you have surgery, you can put this patch in, you can control the progression of your infection, you can mitigate it, and then the chip melts away when you don't need to retrieve it. and you can do wireless lights as well. So my conclusion is that I'd like to think of these ideas that this can be scaled up and that the future could actually have an embedded component to it, where you do have a transition to living materials, where the materials become tunable mechanically and functionally, so that there is a transition between a heartbeat and between the human and the buildings and the object that surround him. Thank you.
Thank you, Theo. And